To me, this looks like it's losing gravity or it's um, losing weight.
This is the most remarkable experiment I think that I've ever done. I'll balance that, first of all, like a seesaw. So there is a balance point. When I take this out here, of course, then the balance point is upset. It should tip down. We know that given the opportunity, it's going to do this if it can, but now we've balanced it, and we've balanced it about its center of mass. So that if this gyro transfers its mass center to the pivot, it should stay balanced. The question is, will it?
I mean, how did it go up?
Well, I mean, there is an explanation for it. It's not super easy, but what's happening is obviously if you just take an average person, say what's different, well, it's spinning like crazy. What you have there is you have atomic structures that are held together. Now, that's what we call by the Coulomb effect, right? This thing. We call it a gravitic force. It's just a small gravitic force. It's faster than the speed of light. It's much more powerful. It's at a different level. That's what we say. But it doesn't matter. It's held together at a stronger force. I guess you would call it the strong force, right?
Okay.
And and as those things are moving, that strong force is way outweighing the gravity field we live in.
Okay.
And with that, you have a momentum and it will pull. It's like a bunch of sailors holding hands on a ship. And I pull that thing is going to have some effect, and it's moving. So if I take a bowling ball on a ship, tie it to a rope, and I shoot that out of a cannon, it's going to pull the boat. Well, we have atomic structure inside these gyroscopes that are being held together. And we put energy to make them move, and yeah, it's spinning. It wants to go out, but those atomic structures, because we made it so cleverly that these things will spin. So you have things. I mean, you have forces all over the place. Yes, and then you have a gravitational field that is variable. It's not equal here to there.
Yeah,
So,
I see what you're saying. Yeah.
So the whole thing is again, until we look at the mechanics and all the forces together, all we're going to be doing is looking at it like magic. It's the same thing as if you give a child a magnet, and they're going to say it's magic. It's a fictitious force. Well, with our model, no, not even magnetism. Everything is a push from some particle somewhere. And there's no charge, there's nothing. It's just a Newtonian world. That is one idea. Doesn't mean it's right. It is an idea. But until you get there, what we are doing is we're making empirical statements constantly. I mean, we measure there's a gravitational force. Does that guy on stage tell you what it is? No. He puts it in a box and says, "Look, it's magic." It's like This is no different from the magician in the 1800s, 1900s, going around doing his tricks, and you have no idea what's really behind or inside, and it gives you the perception of X. Yeah, I mean, you see this. The impressive one is that thing you can't even lift up by yourself.
Yeah, it's got the same principle.
But it's got an immense amount of energy in it going around, being held together by atomic structures that wants to go out, but we've made it in a way that will, it's almost like, this is not a good analogy, but it would be almost like having a bunch of little rockets there, and it's going to be different. But can we explain it? No, because we have not gotten to the point where we go all the way down to those levels, have a mechanical explanation for all of that. And so we're going to, at some point, say, it's funny, it's fictitious, it's magic. I can't understand it.
Can I just throw in 2 cents? When you light a light, and let's say you live in a 60-story building or whatever, you don't worry about, is the electricity going to make it all the way up this far? It's just not a concern, because the the force of electricity is so much greater than the force of gravity. And I just want to point out the force of gravity is tiny, 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 tiny compared to all the other forces that are known. And so what we're doing when, when he's putting up these gyroscopes, and I could get into the details, but it's you're not going to like it. So
no, I want to hear, mainly I want to hear what
my point is
David
this,
has,
the forces that we're dealing with become larger than the forces of gravity. And so gravity becomes a minor player in this once you start spinning things and once you start having electrical stuff going on.
Well, I don't understand how it would, though. But even my question, Greg or David mentioned something. All right, so we have this balance. So we got a seesaw, and we do something with the spin, and it kind of goes like this. Maybe we shifted the center of gravity in the spinning. Is there anything about that in physics? Because
no,
that would do it too. If the spinning all of a sudden changes the location of the center point, it may pivot. It's kind of like in politics, left pulled so hard, now I'm right, and I thought I used to be left.
Well, I just say this, it does matter whether the ring is like hollow or whether it's complete. That's the what is that, an inertial moment of inertia?
Yeah, moment of inertia.
So yes, those things do come into play. They're going to affect it. So
it's not a shift. Okay, let me tell you, it's not a shift in the center of gravity. No way. No.
Moment of inertia.
It's a moment of inertia is describing a force that exists that didn't exist before you spun it. Right. Okay. So that if you want to get to the nitty gritty of the actual reason it goes up this high and all that, again, you're going to have to go back. Okay, what's your model for gravity? How does that affect it at a subatomic level? What is the force that keeps the atoms together? Because let's face it, if I spin that thing super fast, the atoms fly apart. Then what do you say? What do you say? It's so magical that the parts, there's no gravity at all. I mean, it seems absurd, but it's no different from us saying that, when it goes up a little bit, the gravity is changing, the center of mass. No, there's all, like Greg says, he and I may have a different model of stuff, but in our model, we can sit there and explain, okay, because we have all the levels and we can say, this is what's happening. But this idea that what you're trying to do is you're trying to put these high, what we would call in our model the gravitic field 1, which is what we call regular gravity.
Okay.
It's in the middle, and below that is the Coulomb's law, which we call just a second gravitic field because the equations are identical. They're inverse, squared laws. So you have to understand that there's this Coulomb's law, which we say is a gravitic field. The bigger gravitic field, those things interact. Atoms are held together at a certain point. They'll fall apart at a certain point. Your model has to be able to explain all those. But what the problem is when we make those observations, when he puts it in the box, what he's doing is say, don't look behind the box. Don't look at all these different things. Like Greg says, we have different levels with different forces that keep things together. What's really going on is a lot more complicated than just, it's a shift. It's, you can use it that way, you can say it, but the shift in gravity it's not that. That's for sure.
Okay.
So all right. Can I just throw in just a quick explanation? I know I don't want to get too technical, but bottom line, think of I like to think of a skater, out on the ice, and then they start spinning, and then they bring their arms in and they spin faster. Everybody's seen that. That's called conservation of angular momentum. And everybody understands that. Now, if you were to take that same skater and try to move him, tilt him one way or the other, then that angular momentum would no longer be along that axis. It would be along this other axis. That's kind of what's going on. And it wants to do whatever it has to do to get that total angular momentum back. So it might spin around the whole, it might spin around this other axis in order to preserve that angular. It's doing what it can to try to conserve angular momentum. And that's actually what's going on. When you study it from that perspective, a lot of that's explainable from conventional physics.
And the other thing it made me think of what you're saying. What we have is a structure. It's a thing that stays together by itself. We have a pipe, or we have a bar. We have a rod, right, of metal. You sit there. It's a stable thing. You can do a lot with it. You can hit it. You can do it stays together. There's a force that keeps that together. The moment you spin something like that, those atomic structures are still trying to hold on to it, right? I mean, it's still there. So when we're doing just spinning of an object, That's what's happening. If we take a cloud or something that's not held together very well and we spin it, what happens? It goes flying away. Right?
Yeah.
So just the fact that we are, by humans, building these things out of metal that have a very high ability to stay together at the subatomic level, this force, this Coulomb's law that keeps these things together, and we spin it, it's got forces I'm not going to let you go. Yeah, you're trying to, it's the gravitation. Here's an atom. It's got a nucleus. Gravity happens on nucleuses. It has to.
Yeah.
That's what gravity is. So you have this, and I have another one here. In our model, we got these things spinning around it all crazy, and it's got what we call magnetic force that keeps these things. And magnetic force, I won't get into. It's not a fictitious force, but they're staying together. We know we can explain that. As you spin, there's going to be a chance. It's wanting to go out this way. Yeah. There's a force that's inside that wants to keep it. That's where a lot of this stuff is happening. We don't see it. You don't see him saying, okay, imagine all the little atoms at the end and they're trying to go this way. That's why it's pulling that way. But the atoms want to stay together. That's the explanation. But he looks at it at only the macro level in a gravity one field, not looking at the Coulomb.
That's the way I'm looking at it. Yeah. So as an experimentalist, I got something and hey, this is doing what doing this, and I think the theoretical physicist can go ahead and look at it and explain it, to us, the experimentalists, like what is going on. So Faraday came up with this experiment that led to the motors, and Maxwell came and said, okay, I'll explain it. Here's some equations. So I think that the experimental and theoretical physicists, work well together in that sense. So no. I don't think you don't think so. Okay, go ahead.
They're empirical equations.
Okay.
The problem, if I read the back of the book where I'm writing, we're writing right now, it says the problem is that we've been very good in engineering using our flawed mathematics, because mathematics has negative numbers. The universe has no negative numbers. Let's throw that out. That's why you have imaginaries. But we have mathematics, and it's very good for us to predict movements of things. And so we can write equations that describe magnetic fields, or we can write equations that describe how circuits work in electrical engineering. My dad's an electrical engineer. Mm-hmm. We can do all those things. But those equations have nothing to do with the physical thing that's really happening in physics. And what we've been trying to do with the forces, quote 4 or 5 or 3, doesn't matter. The force, the strong force, the weak force, the nuclear, whatever. What we're doing is we're trying to take empirical equations just describing how something moves in a field and saying that we're going to unify that, and that's going to no. It'd be like saying, I'm going to write an equation for you driving a car. I'm going to write an equation for Greg riding a motorcycle. I'm going to take those two very different equations, try to come up with a unified equation for everything. There are equations describing something in a field where we don't have. When we do the balance, what he does with the balance, right? With the gyroscope here, you make your calculations with mass. But that's not what's happening there. Okay. So what you have a whole different system going on. So when you say that Maxwell came up with equations and that the theoretical and the physical come together, no.
Okay.
You have to come with, here's what we say. We have 4 motions, random, going in an orbit, going straight, flowing through, and the other one coming in waves of particles, which is luminic. With all of those, we can build the entire universe and all the equations from gravity to Coulomb's law. Coulomb's law and gravity, it's very easy to show, that comes from a gravitic field. All those equations, Maxwell's equations, the equations we write, the positive and negative, the charge that we pretend that exists, which doesn't really exist. All of those things can be explained by the forces in what's really going on, what light really is, what Coulomb's law really is, what really holds atoms together, what is magnetism. Those are the things that upon which empirical equations, all of electrical engineering comes from that. Of gravity comes from that. All of those equations come from that. So that's what I'm saying. The theoretical and the physical thing aren't coming together.
Got it. All right. Yeah. Okay. So with Einstein, he kind of had this idea, which we talked about or alluded to, but I want to get into it, is that space-time curvature, which always bothered me because space, to me, seems like a hole. How do you have a hole within a hole? Because eventually that's what's going to follow from his equations. So why did he? How? I mean, it's not that I can't understand it. It's just that I don't like it. It doesn't make sense to give a structure to something that is structureless by definition.
You're an NPA member.
Yeah. So space is emptiness by definition.
Yes.
So he kind of came and said, well, that doesn't work, so we're going to give it a structure. Is that right? Is that what he did? Or
no,
did, is that the only
Let
way
me tell you, this is where my linguistics come in, right? I mean, I've spent the last 40 years trying to understand why people use words. If you go to almost every language in the human race, they have a word for space. Its idea is very simple.
Yeah.
Nothing. Now, it doesn't mean that we know that space is full of stuff. We know that.
Right.
But somewhere there's nothing. That's what it is. That's what its definition is. 3 dimensions. We have 3 dimensions, up, down. We know that.
Yes.
Then we say time is a dimension. Why do we say that? Because we can say it. That's it. There's no other reason. It's not because you found it. That's because it is a 4th dimension. It isn't. It's because we have mathematical systems that we use. We put T for time, X, Y, and Z. We'll put T. Okay, there's 11 dimensions. If you look at the physical world, there isn't. You don't go to other cultures and find that there's did you know that in Algonquin in this language they have 4 dimensions? No. So the thing is that you're right.
Missing out all
Space and time. Time is a concept. Space is a concept. They put them together, and somehow that's a physical thing that affects like Greg says, the way light's moving. Of course, it's absurd. It's an absurd.
Isn't time a measurement? People have started to kind of, so then let me ask this then. All right, so time is a measurement. I mean, it's one of the few things we can actually measure. It's one of the earliest inventions. I mean, with a voltmeter and everything, we're not measuring voltage. We're calculating based on the magnetic field measurements, the force measurements. But time is something we can almost directly measure. And distance is something we can directly measure. And you can't mix those dimensions. How did he do that? How did he cross these dimensions into being the measurement of the same thing?
Because he's a scientific poet. He's not a scientist. They talk about these things. You hear,
but you can't do that. Why didn't somebody step in and say?
Because the other people are. Oh, let me tell you. Okay, you want the psychological part of the 20th century? I mentioned this. People were to the point where they will accept anything. I'm not kidding. I've been to art shows where I've looked at something on the wall and didn't know if that was part of the mechanical part of the building or it was art. Why? Because we have made it so that we can allow anything to be anything. And we have gotten away from physics. And I think one of the reasons we call ourselves the natural philosophy is because we're trying to look at what nature is doing. We have to recognize that theoretical is a way that we try to look and give a system to what's happening in the universe. And what we can do in that case is one of 2 things. Look at what something moving and that force and how it's going in this direction and does this. And I can write an equation for the resulting movement of something, which is what time is. Time is movement. If you go to Borkert, he's right. Time and movement. You said time is, you have distance and you can measure that. Time is a way we measure movement. Yes, that's it.
That's what I always thought of it as. Hey, if you like these kind of conversations and you'd like to see more, click like and subscribe to our channel. And if you're at the computer and you'd like to hear the whole podcast, click right here.